Okay, so I've been developing a motor control algorithm called DTC, which stands for direct torque control. So a little bit of background. Here's Wiki, and it's basically three players in the development of this, and that's this guy over here, Mr. Manfred Dappenbrock, and two Japanese guys, Mr. Takahashi and Mr. Noguchi, if I pronounced that correct. So you can see it's been around for a while, so you can see it's sort of in 84, 86, so this is where we're sitting there, so mid 80s. And so DTT is yeah, it's what's that, 18, 90, 20 odd years old, right? Yeah. Anyway, yeah, and anyway, so the guys that sort of took on the challenge of DTC was ABB. These guys over here. Okay, and now 2021, they haven't stopped. So that wasn't a bad. It was very clever of them to realize the benefits of that. So anyway, you can go on Wiki and see this article here. Direct torque control on Wikipedia. Yeah, it's interesting reading. So that's essentially the algorithm over here for DTC, huh? And well, in this article here, they describe it as vector control. I've actually seen it also described as a glorified scalar control, because you can actually achieve DTC without any vectors as well. So anyway, I think Ned Mohan describes that in one of his books in some detail. Anyway, so so this is what I've been looking at developing this. So what you need to do, although it's described as being simple and easy, it's not. It's not simple and easy. So what they're doing is they basically calculating the motor flux by integrating the stator voltage. That's essentially what it is. So so they integrate the stator voltage to get flux, and then they multiply that by the current from the motor going to the motor to get the torque. So there's your two controlling elements, is torque and flux. There it is, torque and flux. And once you've got those two elements, torque and flux, then you can start comparing that against set points. So those are two DC-like terms there. And then you start comparing them against set points. This over here. Now, then we have a controller, which is essentially a hysteresis controller or a bang-bang controller. So it's hard, as you say, on and off. And we have a lookup table to identify what we're going to do with the flux and torque, whether we're going to increase or decrease it. And then essentially we fire a power device, certain timing elements to it. Yeah? That's what this is over here. And that's it. So in that way, it's relatively simple. When you compare it against something like FOC, field orientated control, yeah, then it is simple, yes, for sure. But if you compare it against, say, volts frequency control, well, then it's not so simple. It's more complicated than volts frequency. This is one of the reasons I'm doing this. Is the beauty of the algorithm, and also because it's simpler than FOC essentially, and it performs much better than volts frequency. So That's one of the reasons why I'm using this. So essentially you need to develop that algorithm over there. So yeah, like I said, not too bad relatively. And then you have to develop a motor model, right? Because you need to simulate a motor. This is the motor model over here. It's my mouse gone. There it is. This is the motor model over here. So as you can see, the motor model is much more complex than the than the DTC model. So that's a motor model. There. Okay. So you click this guy and you simulate it basically, and the simulation comes out like this. It's taking a while to simulate, so I'm simulating sort of 0.25 seconds. It's taking too long. So essentially this is what we aim for. So this is the flux on the motor represented in this sort of chordic system over here. So this is the sort of litmus test of this DTC thing. So you can see it's like circular in appearance. So essentially this is the flux sort of going around the stator like that. Okay, and this is these sort of angles over here are the various sections being fired on the power device. So we divide essentially we divide 360 degrees up into 60-degree elements, and then we control the flux in that 60-degree element. Yeah, so within this element, sort of here somewhere, yeah, or here, wherever it is. So look from here to here, eh? And we control that by switching the power device on and off in a certain manner through the use of this bang bang controller, eh? This hysteresis controller. So this hysteresis controller is our controlling element. So we don't have any PIDs in this controller over here. No PIDs certainly means that it's faster. That's what it means. Yeah. So we don't have the pain of having to tune PID loops. In this particular case of DTC, there are other cases where there is actually a PID there. So essentially this flux here is our speed. Huh? That's our speed element. So as a sort of a controls or application engineer, he would sort of be sitting over here. He would be varying at that point over there, and that would probably have a PID function in it. Okay, and the torque element over here, he would be controlling the torque over there. So that would be sort of external. So external to the converter there, you would have some interface to that. So albeit 4 to 20 or milliamps or 0 to 10 volts, 0 to 5 or whatever you choose to be, so that would be a PLC or some type of PEC, programmable electronic controller of some sort. So like I said, so that's telling me that this thing is doing what it should be doing. Okay, switching things on and off, on and off, on and off. Yeah, see, so this is the bang bang controller, something being switched on in that direction, then switched off, and then switched on in that direction, dong, 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 and going around in a circle. So there's an imaginary circle over here, and there's a dead band in between these two, and that's this. So like from there to there is your dead band. It's very small. You have very small numbers over here, and this is the simulation of a very small motor. It's always a 120 kilowatt motor. No, sorry, 120 watt motor, not 120 kilowatt. And so very small values, and these values appear to be right. 0.6 is probably the maximum current of a 120 watt motor, and that's what we do there. And then now the motor model is, yeah, obviously you have to simulate motor model, and this is part of the motor model simulator. So this is the D axis, this is the Q axis, and this is the angular velocity of the stator. So you can see this thing achieved what's it, 1, 2, 3, 5, 6, 7 probably less, within 3 rotations it's sort of more or less stabilized out here. So this is tending towards 0, and this is tending towards whatever, basically. So you can see that looks okay, and this will, so this is radians in seconds basically here, like I said. So you could calculate the frequency of rotation from that. Now, yeah, and it seems to work. If we can run it again, show. It's you know, and like I said, the litmus test of it is this one over here. Let's see if it's going to run. There we go. So there it starts up, and so obviously one turn is let's just say that's one rotation, one turn. And you can see it's sort of tuning in to the its formula, and around about here it should have tuned in, and there it is. So it's actually tuned into that formula at this point. So, and that appears to be quite repeatable as well. One revolution appears to be quite repeatable. So we let that go around. So I think this is a 2-pole machine. So yeah. So so these are, like I said, these are the different vectors that are being fired over here. So if things are looking good, that point there should tie up with that point over here. So let's see if that is the case. And bearing in mind it is actually see it's still tuning in there, stabilizing out, but it is actually controlling. Let's go back there. Oops. Don't want to miss the party. Here we go. So here it is. Now, obviously, the higher this band, also the smaller this dead band, the more switching you have, and also the more circular this appears. So yeah, it looks like it's going to line up. And there you go. It lines up quite good, huh? And I've sampled, I think, 20,000 samples here. So it's now reached its maximum sample size, and it's taken the so it's a buffer basically. So this is the buffer emptying out at the end, and if you follow this point here, you can see it's more or less following the previous rotation, more or less, which is pretty good. There you go. It's zooming there. And the longer you let it run, so the more stable that the motor model gets. The more it tracks. Okay, so you'll see that we should be sort of, yeah, that's the towel end of it. So this is the buffer emptying out on this graph over here. So this is what is this? First in, first out buffer basically. Or no, is it first in? Yeah, first in. Whatever. First in, first out. Okay. So this will be the output there. This is what's coming out. So yeah, that looks a bit peculiar. That. But anyway, let's see how we get down. So we're as you can see, it's tracking closer and closer. So it's locking in better and better, and this is also partly because of the motor model, the way I've done the motor model. This is so I wouldn't give credit completely to the algorithm at this point. So I had a hell of a time actually locking into the supply frequency of the motor. Okay, and I ended up using a phase lock loop. So a phase lock loop does a PID block in there. So this is a PID block locking into the. Well, it's locked in by now. You can see that. If I come over here, this tells me it took 1 revolution for that PID block to, or that phase lock loop essentially, that phase lock loop to lock into the supply frequency. So that's pretty good. But this is not part of the DTC algorithm, is it? As this is not part of the DTC algorithm. This is part of the motor model. And if you're developing this thing over here, you've got as much work developing the motor model as actually developing the equation. That's and the motor model is not I haven't modeled like saturation and whatever, other things. I haven't modeled that in there. There is some load on this motor as well, but as you can see, I don't want to talk about this too much, this parameter here. Yeah. Anyway, so yeah, that's what it is. So it's looking good, and this here essentially, because you can make it better. So let's see how much we've locked in now. We've lost some of that stuff at the end. Oh, here we go. So let's see what we're doing. Yeah, you see, it's pretty good, huh? Oh, it's probably because it's the screen. So, oh, that's right. Is it now? It's over there. So here it is over here. As you can see, it's almost tracking it identical now. Okay, almost. Which is pretty good, huh? Those lines should be parallel, that's right. So this is whichever vector that is there, that looks like probably vector 2 over there. Okay. You can see it is tracking itself quite nicely. So that's essentially a circle. It's just the scaling here and shape of my screen that makes the thing look a little bit not circular, like push it in there a little bit. It looks more like a circle at some point there. Okay, there's 0.6 there, 0.6 there. So that's what you got there. Anyway, so this forms the basis of DTC. So this is a very simple version of DTC, and the beauty of this at the moment is I don't actually need to know any inductances. I can sort of more or less calculate that here, The only thing I need to know at this point is the rotor resistance. Oh, sorry, not the rotor resistance, the stator resistance. That's all I need to know. So I need to know what the stator resistance is and the current coming back from the motor. So that's essentially two CTs measuring the current. And there will be, at some point, we will need to know, why haven't I got that in here? Oh, here it is. The voltage. This is the DC voltage. This is the bus voltage. Okay, and that's what it is. So you write the so you have to write this now into a microprocessor, and then bring it down to the microprocessor, and off you go. And then your problems begin, basically. Anyway, thanks for listening. Cheers, bye.